Good morning or good afternoon, depending where you are. And thank you for joining us for our today's presentation. My name is Zuzana Fabushova, and together with my colleagues, Paul Karam, Director of Engineering at Quanser, and Quanser's R&D engineers, Gilbert Lai and John Pineros, we will be your hosts and webinar moderators today.
Thank you so much, Susanna, and thank you everyone for taking the time out of your busy schedules to join us today. I know this is sort of the end of August, and probably a lot of you are getting ready for the fall term, the ones that have the fall term coming up. And thanks again for joining us here today. At today's webinar, what we are going to be focusing on is how our newly released self-driving car research studio can leverage a lot of the various Mathworks toolboxes that come with many of the that come within MATLAB and Simulink. The one that we will be focusing on primarily today is the autonomous driving toolbox from the Mathworks. I believe they released this toolbox a few releases ago, but it is definitely one that is updated regularly, and there's more functionality as they release it. And this is what we hope to show you, is how we can take one or two components of that toolbox and apply it directly on our research studio. And the more you'll be able to see is, as we work closer and closer with our partners at the Mathworks, is investigating ways to leverage more and more of their toolboxes and various functionality and deploy them directly on our Quanser products. Namely, for today's webinar, my colleagues Gilbert and John will go through how we're taking these advanced concepts in these toolboxes and targeting them on hardware, all the while having the user interface be the MATLAB and Simulink interface, so you can have the insights into what you're developing and into how the whole system is functioning. So with that, I will hand over to my colleague Gilbert, who will take us away and start the webinar. Thank you very much. Over to you, Gilbert.
Thank you, Paul. Good morning, everybody from Canada. My name is Gilbert Lai. As mentioned, I'm one of the engineers at Quanser here. So today, what we would like to show you, as Paul sort of alluded to, is illustrating how we can use some of the tools that our friends at Mathworks provide through their toolboxes, and to use that with our QCar. So let's take a quick step to, for those of you that might not be familiar with the self-driving car research studio, it is our earlier this year we released this solutions that is targeted to be the only validated platform for accelerating, expanding, and sustaining research in self-driving technologies. And to accomplish that, the studio itself is a turnkey package solutions aimed at jump-starting a research program at a location in our users' lab. And the way we've done it is that we provide these turnkey solutions so that they can focus more on the research task rather than more like maintenance and housekeeping tasks that is fairly common in the do-it-yourself type setup that they will have. And by doing so, can help them remain focused and getting to the results sooner, and be able to publish and maybe furthering in their development and validations processes. And on top of that, the easy to use, the quick and accelerations, one of the very useful feature is the fact that the whole system, even though it's pre-packaged, is turnkey, is also open architecture. What that means is completely accessible at all level, from the top level examples to all the low level access to the hardware. It's all open to the users that they can adjust, modify, inspect, and change. And so that is representing a very flexible, expandable, and powerful platform on which to perform research. And this is a indoor setup with a 1/10 scale model car. So that means you can do a lot of repetitive experimentations and development in a very efficient indoor and safe environment. So the star of the research studio is the QCar. So the QCar is as mentioned, a 1/10 scale model car that has a very powerful embedded compute processor, NVIDIA Jetson CX2 on it. In addition, what we have done with the car is that we also added a lot of extensive sensor suites that is built into the car, as well as a lot of IO's capability to enable scaling and expanding of functionalities and modules that might not be, built into the car as well. So things like SPI, plenty of SPI, I2C pins, GPIO pins, additional encoder channels available. On top of that, the mechanical side is fairly straightforward and simple, so it's customizable. So we can provide all the dimensions as needed to fit any additional mounting and module needs. And the hardware, the frame itself has been crash tested so that it's very impact resistant, and you can be sure when using the system, things would happen. We understand, we are part of a research community. Things would happen if you, accidentally slam the car into the wall. It's okay. It's most likely we'll be surviving a few of those before things will get started out of place. And so that means it's robust, it's easy to use, and you can safe to explore and experiment. On the software side, which is sort of what we're focusing on today, we provide out of the box a multitude of different environmental support for development. So, for example, in the out of the box examples that we provide, it would has MATLAB simulator examples as well as ROS and Python examples. And we have application programming interfaces supporting C, C++, and can utilize things like TensorFlow in part of the development. And so in particular today, what we would like to focus on, as mentioned before, is to illustrate how we can leverage the functionalities and features provided by a couple of the Mathworks toolboxes, and see how we can integrate that and combine that with the existing example that we have from the QCar into like different examples to leverage different functionalities, which you can also do with many of the other available packages. So without further ado, I'd like to pass on the presentation to my colleague, John. And here to you, John.
Hello, everybody. My name is John Paneros. I'm a mechanical engineer here at Quanser, and today we'll be looking at integrating MATLAB Toolboxes with the Self-Driving Car Research Studio. So at Quanser, we seek to providing you with the tools for figuring out the answers to your research question needs. As part of training that I've done for AVRS, a common question that I get is how we can modify out-of-the-box examples. And so what I would like to motivate for today is the point of view of someone who has access to our out-of-the-box examples and would like to also integrate some of the available toolboxes for MATLABs in order to enhance those applications. And so I would like to, before we get started, I kind of want to set the problem so that we can figure out how our examples work, what kind of information we're looking at, and then really looking at how we can leverage MATLAB toolboxes themselves. So as part of autonomous driving applications, one starting point is extracting lane information. And so Gilbert mentioned several of the sensors that are available for the QCar. So that would be my first question. What kind of information do I have available? Next, looking at what some of our current examples would be as a starting point, and then really looking at what this new approach would be like for developing my new application, what that workflow would be, so that I can really take my research into the next level. Looking at the vision sensors available for the QCar itself, I've got my Intel RealSense, which is an RGBD sensor. So I can get depth information if I want to detect distances to obstacles that are in front of the car, and also have access to 4 CSI cameras, which are wide angle, give me a 160-degree field of view. And this is the sensor that I'll be focusing on for today for the vision-based applications. So now that I've kind of figured out what my problem that I'm trying to solve is, what sensors I have available for me for image processing, let's look at our starting point. So out of the box, what does the image processing portion of our example entail? So it's a focus on image processing for identifying lane properties. We are, in our standard demo, we're looking at extracting a region of interest from our CSI cameras. Using our Quark blocks, we can do some image thresholding to extract a specific color. In this case, I'll be showing a color for a white portion of the lane, but if I was looking at different scenarios, I could be extracting red or green. And then using a linear polygonal function in order to identify some useful properties for that lane. In specific, I'm going to be using the equation of a line, y equals mx plus b, in order to identify how far away I am from that line and what the slope is so that my car can safely navigate throughout my environment. So how does this approach look like? The first step is taking our RGB image and extracting the HSV properties for it. So HSV image spaces are far more robust and allow me to really nail down what specific color I'm trying to extract. As part of our Quark toolboxes, one of our specific blocks, the video display block, actually gives me very interesting information. I've highlighted here a pixel located in space. I've got its RGB values, but I've also got its HSV values. So when I'm trying to do thresholding, I can really go inside an image and see what its HSV values are and identify the range that is available for me so that I can identify a binary image of my important information. Now, once I've identified this image, extracting my important information, I can now look at my steering angle itself. So how do I calculate my steering angle for this specific application? I extracted a series of pixels. I then fitted them through a polygonal function, polyfit, as we can see as the first portion of my system. And then in my next function, what I decided to do was looking at how I can modulate that slope and line intercept. And so the further I am away from my image, the further my lane gets from me. So I can envision my y-intercept getting further away from me. My slope angle also lets me know which orientation the lane is going so that I can modulate my heading angle. And so by combining the two, I have a way of figuring out, one, how far away I want to track the lane, and also what that angle would be like. And so this gives me an out-of-the-box example for following a lane. But what I want to emphasize here is this is a subset of everything that is happening with the car. As I mentioned, we're using the Intel RealSense, which has a depth sensor, which allows me to identify obstacles that are away from me. I can also choose how far away I can track that obstacle so that I can stop, come to a safe stop. We also have a initial implementation of a speed controller, which uses our encoder values to get an estimate for speed. We're also looking at turning radiuses so that we can figure out when to slow down and when to speed up, depending on where the car is going. And as a research tool, say you're interested in developing your own image processing algorithm, we also give you access to the computation timings so that you can figure out where optimizations are needed as a first pass in Simulink. And then, as Gilbert mentioned, we give you access to C++ code. So everything that you see here gets turned into a set of code that gets downloaded onto the car, and you can really go in and make optimizations in that end. So as you can see in this example, we give you full access, but this would be the starting point. So now that I figured out that my controller is using image spaces, I'm manipulating images, how can we take a separate approach to identifying lane information? And this is where leveraging the Mathworks toolbox comes into play. So as a first pass, let's look at the toolboxes that I'll be using. The first one will be the image processing and computer vision toolbox, which allows me to get the intrinsic parameters for the camera. If you're present in our April Tags webinar, you will know that in that specific example, we're identifying the pose of the car based on an April tag that was in front of me. I used the computer vision toolbox in order to figure out what the intrinsic parameters for the Intel RealSense camera was. And now for this specific application, I'm now leveraging the automated driving toolbox to get access to a bird's eye view. A top-down perspective of the vehicle allows me to get a different view of the lane so that I can identify different information in comparison to the example that I was looking at earlier. And so now looking at the Vision Systems toolbox, there's a camera calibration tool. And so my first step was to get a data set of images. So as you can see here, I took my laptop, I taped down a checkerboard. I figured out the size of the checkerboard itself, of each square, 25mm checkerboard. And with a set of 8 images, I was able to identify pretty much what the focal point was, the principal point, the radial distortion. Since I am using the CSI camera, there's going to be some distortion due to the wide angle nature of the lens. But this allows me to get a full model of this camera on the car. And because each one of the CSI cameras on the car are the same, I could potentially use the exact same calibration for all of them. And it just gives me a lot of flexibility for different type of vision processing applications. One thing that I'd like to point out here is given the data set that I have, I've only used 8 images. Ideally, I'd want to use a lot more images with the flexibility of knowing my projection errors. Let me know which images may be a little too distorted. If I want to keep my values within a specific threshold, and I can export this as a class, which I could then use in my example. So why is having the camera information important? Because in my bird's eye view, when I generate my sensor, my focal point is going to be important, my radial distortion, and my principal point. So what does that end up looking when I transfer it onto the car itself? So now I am on my basement, I'm testing around with the car. And as you can see here, I've transformed the RGB image from my CSI camera into a grayscale image. I am only looking at the lane itself, but what I'm interested in is extracting that region of interest that describes the lane that's in front of me. This bird's eye view then allows me to really take in, and I can hone in into the specific area in front of the car that I'm interested in processing. For my specific parameters, I wanted to look at a distance that was half a meter in front of my car and 1 meter from either the left or the right of the center of the image. One thing to keep in mind with a bird's eye view is the further you look out in front of an image, because of the nature of the transform, there's going to be distortion. So there is some play that you have to do in order to figure out what is that optimal distance that'll allow you to identify the lane information. I'm still using pixel coordinates in this case, as this was the first portion, if you consider, for my overall image processing pipeline. And now we can go back and incorporate it into the QCar itself. So how does that lane information extraction pipeline look like? I am generating my bird's eye view image at the beginning. And once I've extracted a region of interest, I now use my Quark image compare block in order to identify which portions of my grayscale image really represent the lane itself. I've also used a high pass filter in order to get a rudimentary lane detection algorithm going so that I can really identify just the transition in between the lanes. And then using some more MATLAB functions in a state machine, I'm able to figure out which portion relates to my left lane and which portion relates to my right lane. Now, once I figured out that information, I can then, using a polygonal fit as well, figure out what the slope of my lanes are, and then figure out what a heading angle should be. And what I'm going to be passing through to my lane keep assist algorithm is the center of the lane. In this implementation, I'm not biasing myself to either the left side of the lane or the right side of the lane. I'm more focused on maintaining a safe distance from either side of the lane. So what is the output of my lane extraction algorithm? It ends up giving me the following image. I end up getting a filtered image on the left-hand side, which is once I've changed the image through my image compare and I figured out the edges, I can also see the effect of having different widths of lanes and how that would affect that filtered image. And then on the right side, I can see of that portion what is the lane itself, which is coded in green, red, which is the heading angle that the car should be, and a little white pixel, which pretty much defines what the center of the image is. One interesting thing or one useful thing about using the bird's eye view is I know my CSI camera is centered fairly close to the center of the car. So the center of my image is pretty much going to be where my car is headed. And the center of the lane is where I'm going to try to keep. And so using this pixel information, I can now set up a lane keep assist algorithm, which is the next portion of my solution. It's fairly common to use a PD controller and a lot of controls applications. In this case, I'm using a PD controller in order to modulate how far away I am from the lane so that I can safely and smoothly maneuver myself around the test track. I noticed through experimentation that my gains while going slowly were slightly different than when I was going faster. So I gave myself more leniency. The slower I was going, the offset between myself and the center of the lane would allow me to change my heading much faster. Whereas the faster I was going, I was mainly dominated by the lane slope angle, and then the adjustments would be minute. If my adjustments were made to be too aggressive, my car would go unstable. And this is also due to the fact that my camera is on my car. So if I'm moving very aggressively, my image is changing very quickly. The image acquisition is being done at 80 Hertz. So if I start to go unstable, my estimate starts to go or very, very wildly. And so this is why I decided to use this implementation by linearly changing my gains as a function of my forward speed. Now, once I've put everything together, how does my overall example look like? So you see on the left-hand side, the lane keep assist algorithm is fairly similar to the initial one that I started with. I'm not doing any object detection in this case. I'm mainly interested in just keeping the lane. But I can see as I drive around our test track, the car does a fairly good job at maintaining the center of the lane. I can also dynamically change the speed to go slower or faster. And I was able to accomplish this going as fast as 1.5 meters per second. And so we can see just from the bird's eye view, if I play it again, the further away the lane is, there's a little bit more distortion. So I'm fully following closely the segment of the lane that is closest to my car. But this ends up becoming just a small subset where the image processing is the top left green subsystem. The lane keep assist is the right blue subsystem that's with it. And then everything else is maintained exactly the same as I was doing before in order to show what it would be like to modify one of our out-of-the-box existing examples. And so just to conclude and let you know how powerful our solutions can be, we've looked at two approaches for extracting a lane. I've looked at extracting a lane via color and HSV thresholding as one way of figuring out what my steering angle would be. And then looking at a hybrid approach, which leverages the work that's been done by Mathworks in order to develop these toolboxes, which is to expand my applications. Given this, I now have a sensor for my model. And the specific sensor for the camera will then allow me to look at object detection in a far more interesting light, because now I can extract distances from the image, because now I can figure out what my intrinsic parameters are. And so the kinds of applications moving forward can become far more interesting. I was using pixels in order to keep my lane, whereas I can now convert it into distances if my pipeline then dependent on using distances versus using pixels. I've got two sensors on my car which are looking at the lane, the front CSI camera and the Intel RealSense. The advantage of having an elevated RealSense is it can look further ahead than what the CSI can do. So if I was to combine a bird's eye view from both of those sensors, I can get far more robust approach at figuring out what my lane is. And if I was to maneuver around and do some intricate path planning, that is another example that I can do. But this ends up setting up my example pretty much to move on from here. And so hopefully I've been able to paint a picture of what it's like to modify one of our applications, knowing how it was initially designed and what it was looking at, and then leveraging the power of MATLAB's toolboxes in order to make it more robust, give it a different experience, and then use that as a starting point for far more complex applications. Thank you very much. And then with that, I will take any questions.
Thank you so much, Sean, for that very interesting development. This is one of those things that we at Quanser always love to do. Once we release a research solution and a research studio for our customers, our engineers internally are always, one of our first customers, really, where we start taking what we release as a platform and actually trying to apply all the various activities that you, our customers, and our partners in research are always about to do or always doing already. And we try to take some of the most recent developments, and in this case, really looking at all the great toolboxes that the Mathworks is releasing, around image processing, around computer vision, around autonomous driving, and so on and so forth, and extracting from their releases of their powerful tools and seeing which ones can be readily applied directly on our system. We have been working with the Mathworks for quite some time now, and many of our products, the MATLAB Simulink interface is the user interface to that product. And in the case for in this self-driving car research studio in particular, a lot of our forward-looking examples is trying to see what new tools and new offerings from the Mathworks can be deployed directly on the car and on the vehicle itself. All right, so please send us your all your questions, and we'd be more than happy to answer them. We did leave ample amount of time in this webinar to address any questions, any discussions you want us to go down. Let's see. So the first question: did you try exiting the driveway to see how the QCar performs? I'm assuming that did you see what happens if you left the lanes or if it doesn't see any lanes?
Yes.
John.
So as part of the lane keep assist algorithm, I wanted to track whether the car actually did see a lane or not. And so if I ever lost a visual cue of my left or my right side lane, the car would stop. If I had partial information on either the left or the right, the car would keep going. But in general, my safety was if I no longer see a lane, my car comes to a stop.
All right. Yeah, and then to expand on that, because this is an open platform, really it's whatever code you put in. So like John, just mentioned there, he had put in code to, once if there is no lanes detected, then clearly you're off road, if you will, and you should stop. So yes. he's made that decision to implement, but really it's up to you with all the other sensors. You could possibly even backtrack and exactly. Go in reverse until you find where you were and continue that way. Try to maybe slow down if maybe the turn was too aggressive or one thing or another. And so really, when we do release our products, this is a completely open architecture platform. And what we mean by that is out of the box, really, it has no code on it. The expectation is you take our examples as starting code and you deploy that Simulink model in this use case, and that is your full software. The full software stack on the car is in complete control of your model. And so whatever you have implemented in terms of its decision making, in terms of its activities, as it behaves in various states, that's exactly what the car and the whole solution will do. So there's a question here about Python, and yes, definitely. We know that a lot of the research in this field, specifically more on the machine learning and deeply, the learning algorithms, there's a plethora of Python type examples and implementation. And with this studio, we do also support, other software packages like Python, like Cross. And what we've done is taken a sort of a bit more of an inclusive approach here, where because we are very familiar with MATLAB Simulink, a lot of the examples will be MATLAB Simulink dominant, but we are also supporting the other type tool chains, and we've made a decision to allow for the interoperability of those tool chains. So if you have, one research group that is very strong and wants to leverage some of the Mathworks tools, they can be doing that on the studio, while another group or another subset of your researchers can be working, for example, on the Python environment. We have on this vehicle, on the QCar, a Jetson TX2 based processor from NVIDIA, and that has a very powerful GPU on it for exactly these types of applications. And then you can access that power via Python, for example. So it really depends on the preferences and the expertise of your group. But we want to be as inclusive as possible with our support here. All right, I will. Here's another question for you, John. For my research, I focus on planning and control part. Can the Quanser engineer share the individual modules of image processing, like calibration, extraction, and lanes with the users?
Yes, for sure. So the examples that we have available. So if I go back to the video where the car was moving around. So this example would be available for you. Only caveat being is it does require the autonomous driving toolbox, but you can definitely take the little snippets that we have decided here and use it in your research. So if you're interested in the lane extraction portion of the example, you can go in and take the portion that is specific for what you're looking for. Likewise with control, you can look at the lane keep assist algorithm and use that in your research. Or you can also develop one on top and see how yours compares to ours as a way of optimizing or improving what we've done. At the end of the day, we want to give you an example and then really allow you to take it to the next level by implementing the ideas that you have developed.
John, there's one question that I'll field, but maybe in the meantime, if you want to pull up, there's another question someone's asking to actually see maybe the vehicle driving. This is all from the vehicle's point of view. I don't know if you have one that you shot that maybe you can pull up as it traverses the circle that you've created there. And while you look for that, there's this question that I'll sort of field as well. So one of the participants says, "Thanks for the great presentation, John, and demo. Do you have a simulation model of the QCar for developing applications and simulation without the car?" And again, fantastic question. We at Quanser, we're always making sure that all of our systems have accurate mathematical representations, different models through many different paradigms. I mean, Simscape is one example of a paradigm you could use to develop a model or bring one to life. What our vision is, and then this is something that is coming to light now, a big part of it is from the pandemic's point of view as well, that a lot of our research groups who have or want the self-driving car research studio are physically limited in coming into the space and working together. And so with that, we've released a product line actually at Quanser called Quanser Interactive Labs, where really what Quanser Interactive Labs does is provide the exact same sort of sophisticated workflow that you've come to expect from Quanser, predominantly that MATLAB Simulink and then Simulink to hardware workflow. But we've made that available now virtually as opposed to just physically. And so if you want to go on our website, you can, right on our landing page, we have links to all of our virtual offerings. And, you can also expect to see more and more of those virtual offerings, being of our research type platform. So we do envision taking a lot of our research platforms, including the QCar and the full studio environment, and replicating it in a fully immersive 3D environment with dynamic fidelity and capabilities as well. So you can look for that coming down the pipe as we likely in the early 2021 timeframe as well. John, did you have a chance to see if you can have that video of the car moving?
I do have a video with me. It'll just take me a second to organize it.
No
do
problem.
that, maybe I can answer another question.
For sure. So another question, maybe Gilbert, you can field this one. Have you checked driving while there are some obstacles with different shapes and sizes in the way?
Sure. We have tried using the LiDAR to help us detect obstacles. We have, I believe, on our website and our YouTube channels have some early videos of that tests and checks. So in general, yeah, the different sizes, I don't think we have done extensively on image processing as a tool to help identify objects yet, but that is part of the plan. As Paul mentioned before, we have released the platform, but the work is continuing. We'll continue to explore and develop examples and maybe seeding examples to help our users to take advantage of the software and the hardware platform. So in terms of the specifically obstacle avoidance and detection, it would be more moving to come. So at this moment, just the LiDAR ones that we have tested.
Yeah, and there's another question that sort of alludes to that as well, asking about, where can we find these examples, the lane tracking and all the different, various components that John highlighted in this demo. And so really, at Quanser, we believe, again, in making sure that all of our approaches, all the content and examples is public. It is part of the, we want to publicize them. We know that, our belief is always that, yes, there's a lot of great content in there, but truly, to get the best experience, and especially for you as researchers, you have to deploy on accurate hardware and actually validate the research. And so we publicize all our examples for people to look at, and not just take it from us, but also be able to comment on it, and if any improvements are there, or if we're lacking one consideration, we'd love to hear that feedback and improve the full offering for all our customers and all our users out there as well. So we do encourage you to try it out. Just go on our website again under courseware and resources, and you'll be able to find many content and application pieces around the self-driving car research studio just on our website over there. And I see John actually found the video, so go ahead, John.
Yep. So in this video, I'm showing pretty much the detection being done in real time, and then I can see my car driving around as it's going around the test track. And so in this is just for us to be able to see in real time, okay, well, this is how the car is performing. I'm maintaining my lane. I was going slightly slower in this example. I was going about 1 meter per second. I can start it again if you'd like to see. But this was the Simulink diagram I showed you a second ago. This is my filtered image with my bird's eye view. And then I can see the lane being tracked. So I can monitor all my sensors in real time, which is nice because I was able to fine tune my parameters. My PD controller needed a little bit of adjusting, but I can do this all on the fly. I didn't have to worry about preloading and then having the car do 4 loops, for example, and then seeing the information afterwards. So which is also part of the flexibility that we offer, is you can really see what the car is doing in real time, stop it, make adjustments as you need, and then keep going. Just to figure out what does need to be fine-tuned, or if you would like to make a big change, recompile your code and rerun it again.
Thank you, John. That's great. And for those of you who are wondering, the netting is not to protect John from the car. This is also the same space that we fly our drones, which have the same functionality as well, as John mentioned. So that the whole paradigm of deploying and generating your applications in that MATLAB Simulink environment, but being able to deploy that directly on the vehicle. So the actual code is running on that vehicle, but what's happening is the Simulink environment is streaming the data in real time, and you're able to change, like John mentioned, tune parameters, change a couple of switches, and really be able to immerse yourself in the application as it's running, and make the adjustments in real time as you see fit. And this is just one of the roadways, just to mention that our self-driving car research studio comes with a nice cohort, a nice complement of roadway packages that you can configure in very different configurations to achieve the type of scenario or environment you're looking for. Plus, we provide sort of signage. This is a 1/10 scale, so we provide 1/10 scale signage that you can use along stop signs, speed limits, other sort of signage that you can train your car to react to, or to identify and do something about as well. So that it looks like we are at the end of our questions. I don't know if we'll maybe leave it for a minute or so just to see if there's any last minute questions that any of you might have. Again, please sign up to our newsletter if you haven't already, and then we will send you out a recording of this webinar. Please feel free to share it with your colleagues at your institutions. And again, we can't say this enough. We are a feedback company, and we'd love feedback about everything you've seen here and everything we've presented, and any feedback if you are a customer of ours as well on our products and our content that we provide. We're always looking to continuously improve our offering to the market.
With that, thanks again for joining us, and we are looking forward to seeing you at one of our future webinars. Thank you.